Bismillahirrahmanirrahim. Assalamu alaikum viewers. This is me Tehsinullah, and today I'll be presenting my final year project on behalf of my group. So my group mate is engineer Abdul Wajid, and Dr. Shajil Afridi has supervised us in this project. So let's move on. Okay, so these are the contents of our today's presentation. So first of all, I'll be covering the introduction of the project, then motivation, problem statement, then methodology for the implementing of the project and motivation and problem statement, and then review of the existing literature and dimensions, calculation of the desired model, and software used in this project, and so on. And then I'll be discussing about the target of my project and hardware of the project, and for fourth order filter design and results, comparison of the simulation and hardware results, coupling methods for the desired fourth order band pass filter, and the software used in this project, ADS lump circuit of desired fourth order filter, band pass filter, and then future work, and then referencing. So let's move on. Okay, so introduction. So, cellular radio base stations routinely use transverse electromagnetic filters, and these filters are relatively simple to manufacture and offer high quality factor and good spurious performances, and although they are compact inside. Okay, so there are many other filters are also used in this field, but the quality of my filter is that it is compact in size and it offers high quality factor and good spurious response. And here, as you can see that two types of the filters are shown here. This one is a waveguide filter, and this one is the TEM coaxial resonator. Okay, so this is the motivation. So the motivation behind making this project is actually the four important factors, which is low cost, compact size, high selectivity, and resistance to the interference. Okay, so the problem statement of our project is to develop a novel dielectric low-rate filter design for application in the field of cellular communication. And the proposed solution for this problem is we present new designs for the compact air-filled dielectric loaded rectangular waveguide filter with spurious free bandwidth and enhanced selectivity. Okay, so the methodology that we followed in this project is the steps are as follows. The first one is the research and literature review. The second one, filter specifications. The third one is design exploration. Fourth one is prototyping and fabrication. And the fifth and the last one is performance and measurement. Okay, so these are some of the research papers related to our project. So we studied and we took some help from these kind of designs to design our own model. And these are also the research paper, and most of these papers are written by my supervisors, which is almost comparable to my project as well. Okay, so here is the dimension calculation of the desired model. So I use these formulas for the air-filled waveguide. So you can see that here F represents the frequency, A represent the width, and B represent the height of the resonators. And here LMN values actually shows the half-wave variation in X and X, Y, and Z directions. And for my own desired model, I put 1.842 gigahertz value here, and I found the dimensions for my desired model. Okay, so these are the formulas which I used to find the lumped element values. So here, as you can see, the first formula I used here is to find the order of my filter. Here L represent the insertion losses, the LR represent the return losses, and in the second formula, as you can see, the eta is equal to sine hyperbolic of the 1 upon n sine inverse of 1 upon epsilon naught. So this formula is used to find the efficiency of the filter, and here in the third equation, as you can see, this is the coupling capacitor value, which is actually find for the controlling the energy to transfer from one resonator to another. And here is in the fourth, as it is shown here, that it is angular velocity, angular frequency, and the fifth one represent the inductor values, which we will be using in our lumped circuit. Okay, so here software used in the project. So we use two software in this project. The first one is HFSS a high frequency structure simulator, and the other one is ADS advanced design system. Okay, so this is the first order filter which I designed for my practice purposes when we started making our project. So the softwares were new fast. So for learning purposes, I firstly designed this first order filter, which is the resonator. And here, as you can see, the ridge material is used in the middle of this resonator, which is basically the ceramic material, and dimensions are mentioned here. As you can see, this is the top view, this is the side view, and these are the modes which if you can see here, the mode number one is situated on the 1.84065 gigahertz, while the other one is situated on 4.50975 gigahertz, which clearly shows the spurious response of this uh, resonator, or you can see filter first order. Okay, so this is the same filter with the same features. This is the input output coupling, as you can see, and the dimensions are also shown here, top view and the side view. And here on the right side, the results are being shown, which is clearly shows that the first order filter is resonating on the 1.842 gigahertz frequency, which is the center frequency of my filter, which I will be discussing in the upcoming slide as well. Okay, so this is the second order filter which I also I designed for my practice purposes. So the design is the same as the previous, but the only thing that I changed here is the inter-resonator coupling windows. And as mentioned here, that these materials are actually the dielectric bar with metallized blend holes, and the dimensions are being shown here. And these are the result of this second order filter, which is clearly been showing that the result is almost near the filter is resonating to the 1.842 gigahertz frequency. So let's move on. Okay, so the target of my uh, project is actually the design and the fabrication of the higher performance fourth order dielectric loaded bandpass waveguide filter, which offers resistance to the interference and improves selectivity. And the center frequency of the band is 1.842 gigahertz, or you may say 1842 megahertz, which I discussed previously as well. Okay, so this is the fourth order filter for testing purposes. I designed it, and the top view, as you can see, that the width is uniform across all the four resonators. The width is constant, which is 23 millimeter, and the whole length of the filter is 85.5 millimeter. And here the inter-resonator coupling windows are also being shown, and the dielectric bar with a metallized blend hole is also being shown here. Oh, okay, so this is not the final model of my fourth order filter, but this is the testing model. Okay, so this is the result for my testing fourth order filter, which is almost comparable to my final fourth order filter. As you can see here in the XY plot of the S parameters of this fourth order filter in the HFSS software. So here, if you can see that M4 marker is almost on the center frequency of this filter, which is about 1.8449 gigahertz. So it is comparatively good results for my final model of this filter. Okay, so these are some of the fourth order waveguide filter specifications. The first one is the center frequency, which I have already discussed in the previous slides, which is Fc is equal to 1.842 gigahertz. This is the material used in this filter, which is Er is equal to 43, which is the ceramic material, barium titanate. And the bandwidth of this filter, desired bandwidth of this filter is actually from ranging from 1.8269 gigahertz to 1.8921 gigahertz, which almost 65 megahertz bandwidth. And the last one is the design parameter resonator value. The width is, as I discussed previously as well, that this is uniformly with filter. So the width for this filter is 23.7 millimeter, and the length for the first and fourth resonator is 25.08 millimeter, while the length for the second and the third resonator is 21.75 millimeter. Okay, so this is the final model, software model of my fourth order filter. As you can see in the title, fourth order filter hanging windows design, cross coupling. At the top view of this filter, you can clearly see that the hanging window is being introduced in this model. The inter-resonator coupling windows are remains the same, and the direct bar with a metallized blend hole are being mentioned here. And the width of this filter is, you can see that the 23.7 millimeter, and the length for the whole filter is 93.66 millimeter. Okay, so these are the S parameter XY plot of the HFSS software for this fourth order filter hanging windows design. The end band performance of fourth order filter is being shown in this graph, which is clearly being showing the resonating position of this filter, about 1.842 gigahertz. And this is the fourth order filter hanging window design for the broadband performance of fourth order filter. So here you can see that a transmission zero is also been introduced here on the high cutoff frequency, and the end band performance also is remained the same as previously discussed. Okay, so the hardware, this is the hardware of the project, the final hardware of the project. And this is the hardware tuning process when I fabricated my hardware for this design. So first of all, what we did, so we combine, assemble all the parts of this filter, and then we calibrated this hardware through the vector network analyzer device, and then we processed it according to the rules discussed. So we got these results as being shown in this picture. Okay, so this is the comparison of the simulated and hardware results of the fourth order band pass filter. So as here you can see that the results are being labeled, as the black one shows the uh, simulated result as S11, while the simulation, the results of the reflection losses S21 is being insertion loss S21 is being represented by the dotted line, red line. So here you can see that the simulation results are almost being equal to the hardware results. There are some differences, but these results are being acceptable. So let's move on. Okay, so this is the coupling matrix for the desired fourth order filter. Actually, coupling metrics help us to understand the uh, concept of the filter, that each on which frequencies the each resonator is being resonating. So for the first resonator, it is been 1841 megahertz, 0.10 megahertz frequency, and the second one is resonating upon the 1840.68 megahertz frequency, and same, the third one is resonating on 1845.6614. The fourth one resonates upon the frequency of 1841.1083 megahertz. And these values actually shows the bandwidth of the signal energy being transmitted from one to another. As here we can see that the this is the first resonator, and this is the source, this is also the first resonator, this is the second one. So this value actually specifies that the frequency, the signal energy frequency bandwidth which transferred from the source towards the first resonator, so that is at 86.404 megahertz. And this one shows that the frequency, the energy bandwidth transferred from the first resonator to the second one is 78.0591. And same as here, this value shows the same, the energy bandwidth transfer from the first resonator to the second one, it will be the same as the previous one. So these all are the values which actually declares these type of energy bandwidth transformation from one resonator to the another one. Okay, so these this coupling matrix also help us to uh, you know recognize and to tune these kind of resonators to get our desired results. Okay, so in this slide, I have mentioned the ADS lump circuit of the desired fourth order filter, which I designed in my, ADS software. So here, as you can see, this is the source, and these are the coupling capacitors, which are being, declared through the interresonating coupling windows in the HFSS software. So here in the lumped circuit, we actually represent it through the coupling capacitors, while these are the tank circuits, which are actually the resonators of our HFSS model. So what I did is I discussed the formulas in the starting slides for finding the values of these inductors, capacitors, actually to design this lumped circuit of ADS software. So these are the desired results which I got from designing that circuit, which is also been, the center frequency is all is about near to the 1.842 gigahertz, and these are, the insertion. This black line represents the insertion losses, while this red line represents the reflection losses in this diagram. Okay, so the future work. So actually, the modeling of sixth order high performance bandpass waveguide filter with the further improved spurious and selectivity response would be the future work of this project. And the next one is actually the research paper write up or writing in its publication in journal or conference, platforms. So this will be our future work. Okay, so these are some of the references that we search for, and we get some help from these sources. And I as I also discussed in the starting slide, that in the literature review, that many of these papers are written by my supervisors, which is, related to this project. Okay, so thank you for watching this video. Please like and subscribe this channel.